Let's take a look at Big Idea 1 to start our journey getting ready for the AP test. Big Idea 1, we are going to start off looking at atoms and molecules and trends in the periodic table. This is an overview of what atoms are, how they function, different properties, how we know, and how they interact with one another. So when we get into our trends here, we kind of look at the periodic table, and the most important one we're going to look at is size. On the right side of the periodic table, towards the top, those are our smallest atoms. And on the bottom left, these are the biggest. Okay? Because when we get into size, we need to remember that this has to do predominantly when we're going up and down with the number of shells that we're dealing with, and as we go lower on the periodic table, they have more shells. But the odd one is going across, left and right on the periodic table, it's the number of protons. And as the number of protons gets bigger, we have a higher effective nuclear charge, and that means there's a tighter pull on the nucleus, or a tighter pull from the nucleus on the outer shells. So as we go across, they actually get smaller. The right side of the periodic table has these smaller atoms. That is the primary atomic trend to remember. The rest of them are based off of that. The smallest atoms have the highest ionization energies. The smallest atoms have the highest electronegativities. That's the attraction of the electrons and the energy needed to remove electrons, and they have the highest electron affinities because they're the smallest. The electrons are attracted to them. They can get closer to the nucleus, and it's also good to remember that that's an exothermic process when you add things together. The biggest atoms, on the other hand, have low ionization energies. They're really easy to pull the electrons off. They have low electronegativities. They're not really attracted to sharing covalent bonds and sharing electrons. And then they have low electron affinities because the electrons are pretty far away from the nucleus as they are bigger. So the bigger and the smaller ones are really important to remember. The rest of them kind of fill in off of those definitions. So let's define those just so we have a quick discussion on each one of those. Ionization. That is removing an electron. It's harder to remove electrons that are closer to the nucleus. That is an endothermic process. The other one we said was electronegativity. And that is attracting, only the bonding electrons, the shared electrons. And this is really a covalent property. This kind of, the difference between the electronegativities tells us if they're going to be covalent or ionic, if they're attracted enough to pull it completely off, or if they're kind of pulling equally and they have to share it. There's an electronegativity difference there. And then we have electron affinities. Which is adding electrons to make negative ions. And it's good to remember that that's an exothermic process. When two things come together, energy is released. And all of this is, of course, governed by Coulomb's law. which states that Q1, Q2 over R, this is charge and radius. If I have high charges, I have a really high attraction. So this, when we're looking at the nucleus, that's the number of protons we have attracting to the, and how far away the valence electrons are, either of its own atom, if you're trying to remove them, if you're trying to add electrons, how close can they get, or electron affinity, if you're trying to get shared electrons, can smaller atoms get together? What's the attraction between the protons and the electrons in different atoms? Okay, so just a quick trends overview there. And then we get into our PES diagrams. And our PES diagrams, we need to remember that the energy axis is on the bottom, and there's no standard way to report that. You have to pay very careful attention. Where is the high energy side and the low energy side? Those can be reversed. And our y-axis is number of electrons. Yep. That should say number of electrons. Okay. So when we're looking at a PES diagram, we get peaks. And the highest energy ones are closest to the nucleus. And these different peaks represent our where the electrons are in relation to the nucleus, in relation to different shells and to each other. And this is our foundation for electron configurations. So we look at this peak height to say the number of electrons. The closest one to the nucleus is our 1s orbital, and it has a height of 2 electrons. And then we have our 2s orbital. It's the same height, it has 2 electrons. We have our 2p orbital that has a height of 6, because they all have a height of 6. So if we look over here on our axis, this will be a height of 6. 3s has a height of 2. And then this one's a little bit higher, so you're kind of judging here depending on what data you're given. We know that it's at least 2, and it's a little higher, so if we're at 3p, maybe it's 3p3, maybe it's 3p4. You got to judge, is it double the size, half the size, or 1.5 times bigger, a little bit more? You're just making a little bit of a judgment calls, but depending on what data you're given, you kind of make that judgment there. So that's going to lead us to our basis for electron configurations, the energy needed to remove the electrons in every, not only the shells, but the subshells as well. And we talked a lot about those subshell shapes as well. The ones we need to know are the S's that are spherical. And if I have 1s versus 2s, remember that they kind of they form outside of one another. Each shell and subshell gets bigger and forms around the other ones. And then we get the P subshells, and there are 3 of those that we look at. Py on the y-axis, Px on the x-axis, and then the interior in and out of the board, Pz. That's on our xyz plane. So we want to look at the shapes of those guys as well. When we're looking at electron configurations, let's use calcium for example. Remember, this is our map of where all the electrons are in the atom. 3s2, 3p6, and calcium stops at 4s2. So it's every shell and subshell where all the electrons are. We can get noble gas configurations off of these. It's the noble gas that it is isoelectric with would be the noble gas that precedes it on the periodic table would be argon, so we put that in parentheses there. And then we just pick back up at 4s2. And then we can also do ion electron configurations. If we start from the scratch again, 1s2, 2s2, 2p6, 3s2, 3p6, and the ions say, okay, my calcium has a +2 charge. Well, how did it get that? It lost 2 electrons. Those 2 electrons are right over here, 4s2. They're both gone, so we remove them off, and now we're at 3p6. It is isoelectric with a noble gas. When we do that, we can talk about excited electrons when they jump around versus ground state. And anything that follows the rules of our electron configurations is the ground state, that they have to fill up the lowest to the highest shells and subshells, and they all fill up before you go to the next one. We look at core electrons versus valence electrons. And we want to be able to use some of those words. And then the other word we were using was isoelectric. And it's very common for different atoms to be, when they form ions, they're isoelectric to the noble gases and to each other. Just a little bit of vocab to go with those. And then along with that, we also want to be able to draw orbital diagrams. So the last piece of the puzzle here is the spin of the electrons, which is not shown in the orbitals, and the spins are not shown in the electron configuration. The electron configuration shows the energy levels and subshells, but it does not show the actual orbitals and the spins. So for calcium here, we start out at 1s, and it has 2 electrons. We go a little higher, 2s, 2 electrons. Let me zoom in a little bit more to make sure we have enough room. And then a little bit higher in energy, we get 2p electrons, and these are degenerate. All 3 of them have equal energy, so don't forget that word here too, degenerate orbitals. And when we fill them up, it's customary to go up, 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 down, 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 because that's how they would fill if they needed to. 2p's are full. A little higher energy, 3s, up, down, 3p. Those are 3 equal energy orbitals. And this is where we use the word orbital. There's an x, a y, and a z. 3px, 3py. That's 3 different orbitals. So up, 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 down, down, down. And then for calcium, we end at 4s. And you notice I'm not putting superscripts on these. This is 1s, 2s, 2p, 3s, 3p, 4s. There's no superscripts there because 3p6, that's 6, is the electrons. The electrons are up here. They're the arrows. So this shows me the actual orbitals, x, y, z, and the spins of them in each orbital. So just an overview of atomic structure and PES diagrams. All right. We also want to be able to, well, let's go another direction here first. Oop. Okay. With that, some of it, we understand a lot of the structure of the atom by how it interacts with light. So we get a little bit of an overview here of the atomic spectrum. So we want to remember here that the visible range is actually a very, very tiny, tiny range. This is in the nanometer range of we could say 400 to 800. Different places will go maybe 380 to 760 or 780. But we want to understand that that is such a small portion of the electromagnetic spectrum. 400 times 10 to the negative ninth, and that's like 4 times 10 to the negative seventh if you're dealing with whole numbers coming out of your calculator. But what we want to know with the spectrum is the order. We have the shortest over here, shortest wavelength, and then the longest wavelengths over here. And in order, the shortest ones, we do the gamma rays, X-rays. Gamma rays can go all the way into cells and into DNA and do those mutations things, Incredible Hulk type things. Just kidding, it's more cancer. X-rays, it gets through to your bones and your bones block it. UV, they get a little bit longer. They can only go through to your skin, but they do hurt your skin cells and they can burn you and give you a little bit of skin cancer if they get in there. Visible light, of course, doesn't do that. This is where we interact with our world. A little bit larger than that is infrared radiant heat signatures, and then a little bit bigger microwaves, and then radio waves, and they even break it up into FM, AM, and long wave. You don't need to know that. Just the largest wavelengths are in the radio wave spectrum, portion of the spectrum. The ones with the shortest wavelengths have the highest frequency, how often they pass you by per second, the cycles per second, and that is the Greek symbol nu, and they also have the highest energy. The longest wavelengths have the lowest frequency because they're so long and very low energy. We don't expect radio waves to hurt you. We do expect gamma rays to hurt you. They all travel. They all travel at the same speed. All light travels at the same speed. The speed of light constant is c, 3.0 times 10 to the 8th meters per second. So we do need to watch out for some conversions there, meters per second. They all travel at the same speed. Okay, that gives us some of our equations that we need to use on the test. The speed of light is equal to the frequency times the wavelength, and we got to watch out for meters instead of nanometers. We often work in nanometers, but we get C equals lambda nu. And then the energy of the waves that we want to calculate is equal to h nu, that's Planck's constant. And this is what's on your equation sheet, but it's also helpful to know you can substitute the frequency in for the speed of light and wavelength and get hc over lambda. It's helpful to just think about that one as well. So we put those together. And then another important idea over here, when we are talking about these energies in these equations, we are talking about a single electron. A single electron interacts with a single photon of light. Okay, so this idea is important because we often have to talk about more than one. So when this over here, we're talking about what is the energy of a photon with a certain wavelength. That is one single photon that has a certain amount of energy. And one photon will interact with one atom and excite an electron or remove it or whatever it needs to do, but one photon per electron. But how often in chemistry do we deal with one single atom? Very rarely. So we do have the conversions here. Occasionally we need to scale this up. I don't want just a single electron to go with a single atom, but maybe I want a mole of electrons. So we might need to use Avogadro's number to say, okay, well, I have a mole of sodium, and that sodium has +1. It requires 1 electron to be ionized. So a mole of sodium atoms gives me a mole of electrons. I need a mole of photons. So we do need to watch out. The implied units on this energy here are, it's not just joules, because Planck's constant is in joules. It's joules per individual photon, one photon in this equation. And when we do start scaling those up, is when we're going to start to get a little bit larger here. So we are often going to use moles in chemistry, which is very, very familiar to you at this point of the year. When we're talking about what a mole is and we need to scale them up, we have Avogadro's number that we often need to use, 6.02 times 10 to the 23rd. When we have mixtures, we often need to calculate mole fractions. Okay, which is the capital letter, Greek letter chi. How many moles do you have of your substance? I'll say the chi of whatever molecule you're talking about, chi sub A. How many moles do you have over the total moles? This is a fraction, it's not a percent. Don't multiply it by a percentage. Sometimes we do percentages, but it says fraction. And it's not really a fraction either, it's a decimal. You do hit enter on your calculator to say 0.6. The mole fraction is 0.6, whatever it is. And then we often use mass percents. And we get to moles with the ideal gas law, which we'll do a little bit later here. We will talk about empirical versus molecular formulas. Empirical versus molecular formulas. The empirical formulas are our reduced formulas. So H2O2 reduces into HO. That would be an empirical formula, the HO. The molecular formula is the real total formula. It actually is the real one. And remember, they can be both. Water, H2O, is the real molecule. It also is not reducible, so H2O is an empirical and molecular formula. And those are related by their molar masses. So we often use spectroscopy to find, hey, what is the molar mass of my real molecule? It will be some ratio, some portion of the empirical formula. And then to get these, when we have spectroscopy data, we often have mass percents of certain molecules. We need to convert those into grams, usually by just assuming we have 100 grams. You can get whatever sample size you want. And then we convert these into moles. And once we have the moles of everything in our sample, we need mole ratios to say, okay, how does this, how many of these molecules are there to these other ones to get an actual ratio on it. And then if we want the formula, we want the whole number ratios, we have to divide by the smallest ratio, or the smallest number of moles, to try and get a whole number ratio for the empirical formulas. And then we need to sometimes multiply it by a factor, like double everything or triple it, to get a whole number. The goal is to get a whole number. You don't always have to multiply it by some factor if it comes out to be a whole number already. But if it was a 1.5 to 1 ratio, well, that doesn't make any sense. You can't have half of a molecule. So we would say that is a 3 to 2 ratio by doubling everything. And that's an overview of everything that we might want to cover here, talking about atoms and molecules, getting into moles a little bit before we get into big idea 2, dealing with bonding and forces.